is going to be in English because I use a lot of technical terms that I don't know the translation in Spanish, so it's going to be much easier for me. So Sonia, some while ago, asked me to give a talk about some of my research. And I was thinking, okay, should I do some of the stuff Bayesian? But, you know, again, not necessarily it's the interest of everyone. So I decided to do something more entertaining and something more of today. As we know, the discussion of p-values is an ongoing discussion. Should we use them? Should we not use them? The American Statistical Association as well has sent some warnings regarding the use and the misuse. And also I'm going to be talking about the misinterpretation of a p-value and how we should go about looking at it and interpreting it, okay? So why your p-value is less conclusive than you think. So here I have a, wait a second here. So, okay, so here I have a little, so this is one of the contests we had back in the days when Herman and myself, we were doing our PhD, and they set up a challenge for the t-shirt of the department. And this was kind of the logo that won back then. So we have the evolution of statistics, the homo a priorius. So it's an individual that does not observe data or evidence, has his own beliefs. Then the next step is the homo pragmaticus. So he's just very, very, you know, data-driven. He just thinks about X. Then homo frequentistus, which I think we all know. It's more the, okay, so I can combine the two, but I have to condition on my parameter. So the data condition on theta, right? Homo sapiens, so reaches, you know, the light and thinks equally that the data and the parameter can be treated in a similar way using distributions, right? And Homo Bayesianis, and you might ask yourself why Bayesianis, but we had thought in the beginning with another name, which was, yeah, a little bit strange. So we decided to, so here the Homo Bayesianis observes data X, and this is important for the talk because we're going to observe a p-value, right? So that's going to be basically our data. And what we want to do inference is on the parameters of the model, okay? And I guess this next slide, you all feel kind of identified with, you know, just like a football match. We're all excited if, you know, P is 4.9 and if the p-value is 0.051, we are like, oh no, damn, right? Right, so we identify with that slide. So the map of the talk is going to be, we're going to be looking at the caveats of the p-value first. Then we're going to be looking at a simulation example to show you what really happens, right? And at the end, the ASA's, the American Statistical Association's recommendations regarding the use of the p-value. So we all know that Nature and many other journals have applied with those recommendations. And so I thought, since we're all doing research, it would be nice to at least know what's going on. Okay, let's look at what the p-value actually means. So imagine that you have a null and alternative that are equally likely, right? So raise your hands if you think that a p-value of 0.049 means that the probability of error when rejecting the null is 5% or less. So don't worry, I'm not gonna quiz you or anything, but just to have an idea. No? Yes? Yes? Okay, don't be shy. We're all gonna learn here. Okay, so we have a couple of people, I would say more than half, that would say yes. Okay, so what really happens here is we think that we're making a mistake less than 5%, right? But in reality, when we're going to look at the simulation that I'm going to show you, we are going to be at least, this is a lower bound. We're going to be rejecting the null hypothesis at least 22% of the times when it's actually true. right? And that's only a lower bound because that error can go as high as a 50%, right? So I'm thinking right now, we're doing science, just tossing a coin, right? If tail, I accept the null, and heads, I reject the null, right? And so that's actually what we're going to be looking at right now. So, and I want to convince you about that result. And in the presentation, I tried to make it as pedagogical and at the same time very simple, so that at least you can get the simple picture, and that's what I think is important. So if you run the Monte Carlo experiment, so we're going to do a lot of simulations where you run the data from either null or alternative. So we can think before doing hypothesis testing that, okay, I think I could give it a 50-50% that the null hypothesis is the correct one, right? And that's a way to model my ignorance, right? I'm not going to put a higher probability. I'm going to just weigh them equally. So when we run the Monte Carlo experiment and we generate, so half of the times the data is going to come from the null hypothesis, and I'm going to compute my X bar, and I'm going to see if it falls, below or above the critical value that we know in a two-tailed experiment. Or 50% of the time, I'm going to generate it from the alternative, okay? And look at the p-values of 4.9. That's what I'm going to focus on, okay? So if I do that, 20% of those p-values at least will have been creating using the null, basically meaning that I am making a mistake at least 22% of the time, and roughly around close to 50%, right? And I'm going to convince you with that with a nice applet that Germán Molina, co-author of mine when he was doing his PhD, did with his supervisor. So if you get 1,000 data sets, every data sets can be of size 10, 100, as big as you want, okay? And you compute with those an X bar, and you see where the X bar is going to fall, right? So you have 1,000 data sets, you generate under the alternative, and look at how many have a p-value of 4.9%. So actually, since it's a simulation experiment and we're going to discretize these values, we're going to retain all the p-values between 4.9 and 5%, a very tiny little interval, because we know the probability of observing a continuous variable is 0, right? So that's why we need to make this little approximations. Okay, this carries over to all types of hypothesis testing, such as variance. So this implication of the p-value is not just a hypothesis about seeing if a parameter is equal or not to 0. This carries over to all the disciplines as we know them, right? We're running a linear regression, for example. Any generalized linear model, we want to explain another variable and conclude, oh, the p-value of my parameter, beta, is less than 5%, so beta is different than 0. That's the same type of setup where we are all the time. Or we want to do non-parametric statistics, where we want to see, for example, is this density or the histogram come from a normal distribution, right? So we're talking about point hypothesis. When I try to test theta is equal to 0 or any other value, okay? So that's why I want to stress on this, because this carries over to a lot of the stuff we do regarding drug testing, pharmaceuticals. Yes.
Can we ask a question now?
Yeah, if it's a short one, if I can reply it, I will reply it, and if not, I'll leave it for the.
Ask it and then you decide.
Okay.
When you say generate under the null and under the alternative, you
yes.
mean like I generate a variable for all the observations. In one case, I impose a correlation with the outcome variable, and the other one I don't?
No, when I say, well, I think it's an important question. I'm going to answer it because that's going to also carry over the presentation. When I say we generate data sets, right? We're going to do the Monte Carlo experiment. When we only do hypothesis testing with one data that we usually have in our research, that's only one data, right? So we want to look at what happens if I was able to imagine you simulate random variables from a normal distribution with mean 0 and variance 1, okay? So you're going to have 1,000, say, or 100 observations. That's your first data set. Then You toss the coin, 50%. If it falls head, you simulate from the null. Or if it falls tail, you simulate from the alternative. Imagine we toss then the coin, right? So it falls tail. We simulate the data from the alternative, okay? So we're going to simulate 100 data points from the alternative distribution and compute X bar and look under the null if that p-value falls within that 4.9 to 5%, that little interval, okay? And we're going to track only those. Again, I toss my coin, boom, now it's the null. So I generate 100 data points, I compute my X bar, and I see where it falls, right? And I compute my p-value, and over and over and over again, 100 times. So you generate 100 data sets. Approximately 50 of those data sets, or X bars, are going to be computed under the null, and roughly 50% of those are going to be computed under the alternative, right? Is that better?
I we can talk later.
Okay, yeah.
It's only a question about, is there a relationship, a linear relationship between the p-value and that percent? That means if we use a p-value
No.
of 1.01, that means 5%.
No, no. Well, yes, it's so basically the p-value, if you have the p-value you obtain here, 4.9%, the real error that we have here, 22%, is kind of you multiply your p-value times the constant. That's how it works, okay? So depending on the p-value, the constant is going to be bigger or smaller, okay? But the point is, it's not going to be equal to just the p-value. That's the point, the error. And we're going to talk about one thing is p-value, and the other thing is probability of the error, okay? Or error probability, okay? And that's how we should think about this kind of error when we're doing hypothesis testing, okay? All right. So James Berger, who was supervisor of Germán Molina, explains the disagreement among Fisher, Jeffries, and Niemann, the famous Niemann-Pearson likelihood ratio and all of those results, that's Niemann, comes from precise hypothesis testing. So really the big problem is not when you have the null hypothesis, mu is greater than or equal, or smaller than or equal, right? It's just when it's equal. That's when this kind of problem comes. And that's basically most of the problems because we mostly use this type of hypothesis testing, the precise. And that's what we mean with precise, a parameter being equal to 0 or being equal to any other number. So the setup, we're going to assume we're going to simulate some random variables from a normal distributed random variable with mean mu and variance sigma squared. And the hypothesis is going to be mu 0 versus mu different than 0. Okay, a very simple setup. I think we all teach this class in undergraduate, right? So here comes the p-value. So computing the p-value as probability that given, right, I have the H0 here, given that H0 is true, the probability that I observe a more extreme value, so this T of X is, just think of it as X bar, okay? And this little T of X, just think of a small little X bar that you observe from the sample, okay? That we generated. So this can be seen as an index of the strength of evidence against the null, where a small p-value show how unlikely the evidence is in favor of the null hypothesis. But don't you think that we would prefer something like the probability that given that I observe this p-value, that the null is true? I personally think, I don't know if you guys know about alopecia, people that lose their hair, right? Well, imagine you want to develop a test to see if somebody can develop genetically alopecia, right? And looking at the definition of the p-value, if the null hypothesis says the person has alopecia, what's the probability that the test works? But that's obvious, right? If the person doesn't have any hair, I mean, it's useless, right? And in a way, I want to show with this example and to connect it with the p-value, we're already assuming that H0 is true. But that's the whole point. We don't know if it's true. We're assuming it's true, but we want to know if it's true, right? So the same with someone with alopecia, if, you know, still have hair, but you want to see if you can develop that. Well, given that the test, imagine I do the test for alopecia, the test was positive. What's the probability that I do have alopecia? Or going back to, you're going to do your blood exams, right? And you want to see that if you have an illness or cancer or whatever, right? You don't know, or if you're going to develop cancer. Well, it's easy to see once the person is ill, right? But that, I mean, you already know, so there's no point, right? The whole point is try to guess if someone is going to have that or develop that illness, right? So you cannot condition on the person H0 has the illness. You have to twist the probability, right? And this is why I write, we prefer something like in the slide, given that we observe the p-value, right? Now I want to know if the null hypothesis is true, right? That's what really is useful for me, right? That's like, if I condition like the p-value is like the test came positive for alopecia, what's the probability that I will develop alopecia, H0, right? Or alopecia is true. And that's why a lot of times you make an experiment, blood experiment, and the doctor tells you, hey, you know what? You should do another exam. That's just to be sure, right? And that's what usually happens. So we want to have, sorry for being so passionate about this, but the probability that given the p-value observed, p, probability that the null is true instead of the other way around. So it's like probability of A given B instead of probability of B given A, right? And that's what this is all about. Okay. So a wonderful illustration is developed by the applets of Germán Molina. So I'm going to show you, and we're going to run it so that you can see. It's kind of a nice illustration. The applet assumes this normal hypothesis testing, simulates the proportion of times that H is true when the p-value is in the range from 0.49 to 0.05. So we're going to simulate a lot of times, right? The null, tossing a coin. So I generate from the null some data set, right? I compute from that data set X bar. I compute from that X bar a p-value. And I look, did it fall between the interval 4.9 and 5%? Yes, no, repeat. Next time I simulate from the alternative, generate a sample size, compute X bar, compute the p-value of that X bar, and I see if it falls in these ones. And those are the ones that we're going to keep track of, okay? Because then we're going to condition on the p-value being that value, right? So we want to keep track of only those p-values that fell inside that small region, right? Okay, so the applet simulates a big series of such tests and tracks how many times H0 is true given or conditional on that p-value being in that interval. So half of the null hypotheses are initially true as well as alternatives, as we said. Among the tests where H0 is true and P is equal to that number, at least 22% and actually over 50% of the true H0 will be rejected. So imagine the consequences. Okay, so this we already saw, right? I'm going to go over this slide as well. We already also, okay, another thing. If your p-value was 4.9, then your p-value is not any value less than 5%, right? Why? Because you observed 4.9. You didn't observe 1%. You didn't observe 0.5%. You observed 4.9%. You cannot condition or say that it was smaller than all the other ones. That's a kind of misinterpretation, right? And so we're saying that if a p-value is 0.000001, we are comparing it as well with a p-value of 4.9% just by saying, oh, p-value is smaller than alpha, right? It's not true. It's the same, different types of evidence, right? So this is a common drawback when using error probabilities. Miguel.
How can you decrease this 22% when you find a way of 0.49?
How can we're going to see that in a slide. I'll come back to your question. Okay. So So p-values, just to understand, and probabilities are not the same. So this is the applet. We're going to go and run the applet. So this is the address where we have it, right? You have it, if you want to use it, you're welcome to use it. You just have to install the cheer pj applet runner in Chrome, okay? So let's go to the Chrome and do a little experiment, right? So here I have the applet. Can you all see, by the way, those in Zoom, my Chrome applet? I think they can.
Sí.
Okay.
Sí.
Okay, thank you, Aneta. Okay, so we have here, we're going to use a sample size of n equal 10, okay? 100 is going to take much longer, and we're going to use the distribution of the alternative is a normal distribution with location 0, mean 0, and scale 3. Meaning that when I generate from the alternative, remember the alternative is mu different from 0, right? So how can I do that? Using a prior distribution that is centered around 0, and it's going to take some mu's that are going to be positive and some mu's that are going to be negative when I'm going to generate the data from my alternative, okay? So that's why we have that. And as you can see here, you have an array of possibles, possible alternative. You can use the t-student, the uniform, the normal, the Weibull, exponential. There's a lot you can play with in this little thing. And we're gonna, so the percentage true or nulls here, we calibrated to 50% and p-values from 4.9 to 5%. So let's do the little experiment. So we press here on continuous, right? And let's wait. So this is not C++, a super fast computer, but I'm going to leave it up to, let's say, 1,000, right? Data sets that I'm going to generate. And we're going to look at those probabilities of mistakes, the probability given the p-value that I observed, which is between 4.9 and 5, right? How many times did I reject the null hypothesis, right? So we're getting close there. Running 600, right? Okay, let's wait for 1,000, and then I'll end simulation and we'll get the results, okay? Okay. So the winner is, so we can see here that we rejected the null 57% of the time when it was actually true, given that my p-value was 4.9, okay? We can obviously play, now going back, Miguel, to your question, you can obviously play. If you put the percentage true of nulls to 10%, right? You're actually biasing that probability and you're introducing information, right? Because if you say only 10% of the times the null is correct, then of course this probability will decrease from 57.18 to something smaller, right? But you don't know a priori necessarily when you're going to do the experiment. If this is only, well, you can also play with the p-value. I can give you the stuff and you can play around and simulate it, right? So if you're interested.
Yeah, but I wonder how quickly it decreases.
We're gonna look at the curve, right? So the smaller the p-value, well, the smaller the error, not 57%, but still is going to be significant. Even if you have a p-value of 0.0001, you might end up having this probability of rejecting H0 true, given the p-value that you observe, around almost 5 to 10%, right? Which is quite significant, right? Yeah. Okay, let's go back to the slides.
How does that vary with the type of distribution that you're using?
How does that vary? The sensitivity analysis is not that kind of much, really, right? I mean, it's going to vary, but it's not something you would say, oh, then let's use the normal. It's something that is generalized, right? I mean, this is a real problem of the p-value, not of the distributions that you use or the assumptions, right? It's a pending value with any distribution you use. Hypothesis testing, precise one, equal, right? That's a problem, a generalized problem, okay? And this is the lower bound. So look at this graphic. This graphic was taken from Zelke et al. 2001. Remember here in the x-axis is the proportion of times the null hypothesis is true, right? So we were what, at 50% roughly here? So if we read here 50%, we get closer to this 20-something%, right? But it just tells you, or just gives you the lower bound, right? Doesn't say so. You know, the error probability can actually be much higher. This is like a conservative lower bound, which is, in my opinion, already low. Going back to your question, Miguel, if your prior is 10%, then of course this is going to be small. But how do you know the prior has only a prior probability of 10%, right? I mean, nobody knows. Okay, so ASA recommendation. So this is what they have published in Nature, in all these discussions about should we use not the p-value. So the p-value was never intended to be a substitute for scientific reasoning by Ron Wasserstein, the ASA's executive director. Well-reasoned statistical arguments contain much more than the value of a single number, and whether that number exceeds an arbitrary threshold. The ASA statement is intended to steer research into a post-p smaller than 5% error. So we have to move on, guys, right? That's what they are. That's a recommendation. If you observe a p-value of 4.9 and you jump to conclude that because alpha is 5%, you can be confident H0 can be rejected. Be aware, first of all, how many papers you will be wrong. At least 1 in 4 papers you will be wrong, right? A false conclusion, right? Not only that, over time, it appears that p-value has become a gatekeeper for whether work is publishable, at least in some fields, said Jessica Utz, ASA president. This apparent editorial bias leads to the file drawer effect, in which research with statistically significant outcomes are much more likely to get published, while other work that might not well be just as important scientifically is never seen in print. Why? Because the p-value was bigger than 5%. And it might happen that that paper was a great breakthrough, and the person just stored it in a drawer thinking, oh, I'm going to throw my research. So that's the negative side of the p-value that it has generated in all the research we do. It also leads to practices called by such names as p-hacking, right? That emphasize the search for small p-values over other statistical and scientific reasoning. What is p-hacking? Is basically you fit the data, the noise of your data to the model, and then you get, yay, I got a nice p-value, right? But what you're just doing is fitting the noise of your data in the model, right? And then to do prediction, that's going to be a horrible model to use, right? That's the drawback. So 6 statements which are important to conclude the talk. The ASA statements 6 principles, many of which address misconceptions and misuse of the p-value, and are the following. P-values can indicate how incompatible the data are with a specified statistical model. P-values do not measure the probability that the studied hypothesis is true or the probability that the data were produced by random chance alone. Scientific conclusions and business or policy decisions should not, and this is really I stress that, should not be based only on whether a p-value passes a specific threshold, right? Proper inference requires full reporting and transparency. A p-value or statistical significance does not measure the size of an effect or the importance of a result or a variable. By itself, a p-value does not provide a good measure of evidence regarding a model or a hypothesis, okay? Thank you very much. Giorgio.
Thank you, Enrique. I was wondering, so if you would test the predictive power of your model, I have 2 questions. This is the question. So if you would test the predictive power of your model, suppose you run your regressions and your multivariate regressions, and then instead of focusing on the p-value, you say, okay, why don't we actually test if we can predict Why?
So smart guy, Giorgio, yes.
You will not, I mean, you will realize it, I mean, maybe not certainly, but you will get a sense of this type of problem, right?
So I would not use a p-value to see if I'm going to put it in a model as an independent variable and do prediction for that. First of all, we agree on that. Second, I would try to do a cross-validation, right? There is some sort of, but that does not, well, I'll talk about it later. And then I'll do out-of-sample validation, right? So you take your data, you take a k-fold, and you take it out and you do a lot of times and you see the histogram of your out-of-sample R-square, for instance, okay? That's what I would do, exactly. Then there's another method called Hochberg, something regarding the p-values. I forgot the name, that in a way tries to tackle this, not exactly. It's some sort of, you know, when you have a hole here and you put a patch here, something like that from a frequentistic point of view. So I would do more something like that, not go through the p-values and do R squared out of sample, and that would be fine, for instance. Yeah. Any other question? Sonia.
Yeah, you say that some journals are already moving to abandoning these p-value as a criteria, basically to select which papers they publish or not. How long do you think it will take for other areas, like really to catch up? Because right now this is what is happening, it's pretty much everywhere, right? If you don't get a p-value less than 0.5, then you're done. So like, how long do you think these will take?
Wow, that's a hard question. I personally don't know. I do think, however, 30 years ago, James Berger, Herman Molina's supervisor, was the first to point this problem regarding p-values. That was 30 years ago. Then nature caught up and does not accept, studies with p-values. Some other journals, I don't know. I think if you try to, well, this is a reason, let me put it this way, Sonia. This is a reason why I'm a Bayesian statistician. I don't have to work with p-values. Thank God, right? So that's why. If you ask me, that's my reason, right? I don't know. I really don't know. I think perhaps 20. So let's take the 30 years from James Berger and then let's put like 30 years more, perhaps 30 years more, something like that.
Yeah, and the reason I'm asking is because it seems to be such an accepted practice that I could see the resistance to change for everyone that uses a p-value as a criteria, right?
Yeah, there's going to be a resistance. However, I have a friend in a business school, a business in Norway, BI, I think. They had to, all the professors undertake a course in Bayesian analysis. And they were going to help them and, that all that stuff. But that's all I heard so far. And that was 2 years ago. So I don't know. But yeah, I don't know what's going to happen. Definitely, I don't. But I think there's other ways like what George just said, trying to avoid. I don't think we're going to, frequentist statistics or classical statistics is going to disappear. I think more we're going to try to look to other routes other than the p-value and perhaps define something by then. So don't give hope. So, right? So that's yeah. Giorgio, do you have another question?
The other one was practically since I think we have talked.
It's raining, right?
So if you would like to do this type of test like we did in the applet, but with a multivariate regression. Okay?
Yeah, okay.
So suppose your data set is 4 variables, 1 outcome, 3 independent. And your modeling mind, you run your test. And then normally you would focus on the provider and say okay or not okay. But then you want to actually test the way you did it with your applet, but now with the model and the data. So how would you simulate the data set in this case? Would it be by doing these k-means or breaking it in another way and simulate it a couple of times? Or would it be by saying, okay, each variable has a certain distribution, so I sort of reshuffle things and then rerun the direction and then see what the value gap or how we do?
Well, the best way to do it, this is what we saw in the applet, a Bayesian simulation. So we're doing Monte Carlo simulation, integrating out the parameters in some ways. You can see it as a Bayes factors, numerically speaking. In this other way, there's no escape, right? The best way would to do a linear regression with Bayesian coefficients where you look at the posterior distribution of your betas. And for example, you see how away the tails are from zero. And that's a sort of Bayesian p-value, if you want to call it this way. If the posterior distribution of your parameter is centered around zero, you cannot conclude it's different than zero. But if this is zero and this is a normal distribution, if I shuffle it this way, then there's a very tiny probability of being zero or less, or this other way, if I put it, right? It has to be up or down, but almost not include the value zero, then you can conclude my parameter is statistically significant different from zero, and it's positive, right? Miguel.
How do you adapt this? So what do you think would be the new frame, for instance, with experiments?
The what, sorry?
With experiments, a new frame to deal with these issues if you are trying to do an experiment. Because in experiments, you will have just one possible database that we would collect.
Yeah.
You don't know the distribution for those for where it comes, and you don't have other observations to run.
So a way that you could use is, for instance, Bootstrap, right? If you want to resample the data, or being just, non-parametric and asking yourself what is the non-parametric density of this stuff, doing kind of a Bayesian analysis, for instance, or Bootstrap classical analysis, if you don't want to do Bayesian. Right? And you want to see with that only data set, if you resample it with replacement, what is the, Monte Carlo errors of, the whatever values you're computing from that experiment.
Another one. Because the that p-value is not in terms of reliability, there is the same situation for the first. That means the reliability is very important to the
Okay. Thank you.
In terms of, for example, there are ways of the work. For example, if you don't have the data, you don't have ways of actually doing something to prove your robustness of your data because you're able to do the work. How do you recommend to assess another person like results or conclusions based on robustness tests based on this kind of things?
Which kind of things? Based on what kind of?
Based on this kind of, for example, if the person is including something about, for example, based on the data. For example, they run a regression or something like that, and they conclude based on just the data, or they do some statistical representation.
Well, there's a test which I think, but I don't know if the essay. Well, again, as I said, it's again using p-values, and I'm not really fond of that. Depends on the context. And our ASA's recommendations does not say that you cannot use the p-value. It's just that you cannot say p is less than 5%, right? So p is just an x bar, right? You cannot, if x bar is 10, you cannot tell me like x bar is less than 20, right? I mean, I'm not interested in that, right? X bar is 10. So you can still write in your paper the values of your p-value, but stating that, for example, like George just said, doing a robustness test in terms of the forecast or the R square, where, for example, imagine you can get with those variables and take them one by one. Of course, it's going to take some time, but then keeping the most parsimonious and with the less amount of variables, but that performs a fairly good R square, right? So that's a way of kind of not throwing away what you did, but not concluding. A p-value is just a necessary condition, but not sufficient to conclude that, yes, this causes this, or this does this, or this is equal to this, right? That's just a sign of warning. So it looks like the rain never stops. More questions? So this is the bibliography.
¿Alguien tiene preguntas? Aquí en la audiencia física no hay más preguntas. ¿Alguien tiene preguntas? ¿No? Bueno, pues muchas gracias a todos por su asistencia y preguntas. Gracias, Enrique, de nuevo.
Muchas gracias a todos ustedes. Un placer.